All right, so what are dBs? Again, dBs are decibels. I think that it's typically written like this, but it would make probably more sense to note that the unit that we're talking about here is actually the bell, right? The bell, which is a unit to measure ratios of power. So we haven't talked about power yet. This is sort of irrelevant to what we're actually trying to do with decibels, but the actual unit is the bell. And so the decibel is 1/10 of a bell, the same way that a decimeter is 1/10 of a meter. A decibel is 1/10 of a bell. So I think that that's important to note. So first and foremost, if we want to get from bells to decibels, we need to multiply by 10. The same way that if we wanted to get from meters to decimeters, we would have to multiply by 10. And so that's a key concept to understand here. Let's just keep that in mind. The other thing that we need to understand is power, which I haven't talked about yet up to this point. It's the next chapter of this class is all about power analysis, and I haven't talked about it. Probably should have talked about it in EE 220, but I neglected to do that because I knew I was going to talk about it in this class. I have some resistor here, right? If I have a voltage across this resistor, V, I can determine the power dissipated by this resistor in watts, which you've heard of, by taking the voltage across it squared and dividing by R, okay? So that's important. Just keep this in mind. That is an aside, and we're going to use this, the fact that power dissipated is equal to V squared over R, okay? It's also equal to, if I have the current flowing through this resistor, it's also equal to, let's call this I, it's also equal to I squared times R, both of which are important for what I'm going to do next, okay? So don't worry about this right now. This is just part of my derivation. We're not talking about power for the sake of anything other than me deriving where the decibels come from and why we do what we do when we do Bode plots, okay? So let's say I have some ratio of powers. I have a system here, some system. It might be a circuit, it could be a communication system, a transmission system, whatever. And it has some amount of power, P in, flowing into the system. And then it has some other amount of power, P out, flowing out of the system. And then this is just some system, or it could be a circuit. All right. If I wanted to take the ratio, right, we've been doing this up to this point, the ratio of the output power to the input power, I could call that my gain, or G, my power gain for this particular system. We talked about voltage gain, we talked about current gain, we talked about transfer functions, right? Right now I'm interested in power gain. And this is what people at Bell Labs back in the day were interested in characterizing, was power gain for communication systems. And so what they did was they decided, because humans perceive sound, and specifically for communication systems, humans perceive sound logarithmically. They decided that they were going to take the logarithm of this ratio, which is the log of P out over P in. Okay, and again, this is base 10. I'm not going to write base 10 every time. I'm going to write it here, but from now on, just assume if I write log that it is base 10. Okay? And if I want to get this unit now, which I have in bells, right? This is in bells. If I want to get that into decibels, I need to multiply by 10, like I said. And so this basically, just note that the unit bell here that I wrote, it was created for this measurement, for the logarithm of the power gain of a communication system. So this is, by default, this is in bells. So if I want to get this into decibels, I need to multiply by 10. So the gain in decibels is equal to 10 times the log base 10 of the power gain. Okay? Lastly, remember that I just said the power was equal to V squared over R, or I squared times R. Okay? So if instead of measuring power gain, I'm interested in measuring voltage gain, right? Which is what we're actually interested in, right? In all of our plots here, we've been so far interested in measuring V out over V in, right? The voltage gain of the system, V out over V in. And that's what we were looking at when we looked back at these circuits, right? V out over V in. That's what we've been interested in this whole time. So to get from decibels and the power gain into voltage gain, this is what we need to do. We need to convert these powers into voltages. And how do we do that? Well, I can note that the gain in dBs is equal to 10 times the log base 10 of the output power of my system, which would be V out squared over some resistance R, divided by the input power of my system, which would be V in squared over R. Okay, well, my R's are going to cancel here, so I'd be left with 10 times the log base 10 of V out squared over V in squared, but I could just square the whole thing at that point, just like this. And if I remember, right, this is my gain in dBs. If I remember my log rules, I said that the log of x to the n is equal to n times the log of x, right? I can take this n and basically pull it out as part of my log rules. And so I'm going to do that. I'm going to pull this 2 out. And what I'm left with is that my voltage gain, not my power gain anymore, my voltage gain in dBs is equal to 20 times the log base 10 of V out over V in. And so this right here is the key to Bode plot magnitudes, is that we are going to be plotting when we do a Bode plot so that we can get these nice straight line plots, we're going to take our V out over V in that we found, and we are going to take 20 multiplied by the log of that ratio. And that is going to give us our gain in dBs, okay? So take note here. If I have V out over V in is equal, right? V out is equal to V in, I would have a value of 1 here, right? A value of 1, which means that they are the same. My output and my input voltage are the same. We know from log rules that the log of 1 is always equal to 0, right? So if that's the case, then that means at V out is equal to V in, right? For V out equals V in, my gain in dBs should be equal to 0 dBs. All right, let's go back to our plot that we had here. What is the case when V out is equal to V in at low frequencies? It's 0 dBs, right? Okay, so that's awesome. And then let's try one more point before I end this video. What happens if my V out over V in, right? So this was V out was equal to V in, or V out over V in is equal to 1. What happens if my, What happens if my V out over V in is equal to 0.707, which was the cutoff frequency for our previous circuit, which was 159 hertz? What happens? I'm going to take 0.707. I'm going to take the log of that, and I'm going to multiply it by 20. And what do I get? I get roughly negative 3 dBs, okay? So let's go back to our plot at 0.707 at 159 hertz. What is the dB value? 159 hertz is like right around here somewhere. Let me actually pull out a red color here. Let's just say it's like right here somewhere. I'm expecting to see negative 3 dBs. Okay, so it's halfway between 0 and negative 6, which would be exactly negative 3 dBs. And so not only is this frequency often called the cutoff frequency, right? It is also called the negative 3 dB frequency, or sometimes just shortened to the 3 dB frequency of the filter or of the circuit, okay? And that's why, because of course this is where V out over V in is equal to 0.707, and in decibels, that is a value of negative 3 dBs. Okay, so hopefully this is clear. If it's not, obviously feel free to ask some questions. But I just wanted to get to the point where I derive why are we taking 20 times the log of the V out over V in. Because when I took this class, it was just thrown at me that in order to go from V out over V in to dBs, we just need to multiply by 20 and take the log. And to me, that just seemed so arbitrary. So I wanted to show you the reason why we do this. It's because originally they were looking for power gain. They were measuring the log of the power gain in bells to get to decibels, which is a more useful unit because it's smaller. You have to multiply by 10. And then to get voltage, which is what we're interested in, voltage gains and current gains, because the same would happen for I squared R, the 2 would pop out. We have to pull the 2 out and get 20 out here instead of 10. And that is where this equation here comes from, which is going to be very useful moving forward for drawing our Bode plots, okay? So I'm going to go ahead and end this video here. This is probably a lot to digest. Please feel free to ask questions if you have them. And I'm going to go ahead and end this video, and let's see what's next. Oh, in the next video, I'm going to be doing an example. So hopefully things get even clearer when I do the example with the same RC circuit that we've been working with this whole time, okay? So I'm going to go ahead and actually let me just move this over here to just keep things neat. And I'll go ahead and end this video.